I've made games for Sony, Microsoft, Nintendo, Apple, and many more on their various platforms. Move this on. This is not me. This is me without the glasses. So let me get started. So I should have put that on before that slide. There we go. So that tells you a little bit about me. Okay. So it's been quite a while since I gave a talk on video games. I don't think I've ever given a talk on AI in video games. Ironically, all right, yeah. So I was asked to give this talk. I thought it would be a great opportunity to consolidate what I've experienced in the last 20 years or so of game development. I've worked with many of the AI technologies that I'm going to talk about in the early part of this talk. But later on, in the later part of the talk, there's some techniques I don't have any direct experience of, but it's been, as I said, it's been a great opportunity for me to kind of look through all that and consolidate what I've experienced. So when I talk about AI, I'm not talking about the technique, but I am talking about the techniques, algorithms, and applications that appear to have intelligence. AI, though, is not about creating a human-like player in the game with something close to real intelligence. You probably expect that because it is artificial intelligence. Artificial intelligence is fabricated by humans to make a machine appear to have some life. A good way to think about this is for our in-game algorithms to present a perception of intelligence, to appear alive. A philosopher might begin to argue what is intelligence. Maybe it's a function of intent or something like that. So, you know, when you start looking at AI, you start thinking about what is real intelligence anyway. But I won't get into that. The intentions that we give the machine could be to, say, challenge a player, to be a challenging opponent for you as a human. And that challenging opponent is there to win a game according to its rules. It could be to support the player in making their own winning moves. It could be to personalize the experience. So we could use AI to generate worlds in response to players' actions. And it might be to identify almost imperceptible variations in what it senses and respond in ways that will give it the best reward. And it's these rewards that we choose. So just prior to leaving the games industry, I was working with data analytics for hyper-casual games, and it was becoming clear that AI was important to these aspects. And these aspects are outside the actual video game opponents. So most popular mobile games regularly have tens of thousands of daily active users. And thus, analyzing this data naturally adopted the new kid on the block, which is machine learning. So we'll look at some machine learning as well. This technique develops a sense of what is driving players to make those microtransactions, those little purchases in game, a few pence here, a few pence there. And it's a key factor to retain players in games and for predicting that user behavior. So there we go, that's it. Okay. So AI techniques are used in many different areas. So there are many more aspects I could be talking about today, but I don't think I will have time for any of that. So what I do have will hopefully give you enough flavor of artificial intelligence in video games to pique your interest. I'll work forward in time to present these ideas. So I'll start with traditional AI, and that works well where there are a limited number of rules and information about the whole state of a world can be interrogated. Quite quickly, the game rules and the state of the game become a little bit messy, and it becomes unfeasible to use these early techniques for playing games and being AI for games. So to keep some control over these opposing players, the opposition player, decision trees and finite state machines are employed to provide a challenging experience. These form the basis of pretty much all non-player characters in video games. So these first two things here, traditional and bots, I've called them, are basically what's doing most of the game AI you see, which is why I could have given a talk entirely on these algorithms, but I decided to kind of maybe take it a little bit further. I'll introduce machine learning, as this is quite exciting, as it can recognize cats, translate languages, and beat the best going chess players. But rarely does it ever drive non-player characters in games, and you'll see why when I get through the talk a little bit later. I'll talk about how it's used in recommending game features, these recommendations, and I'll talk about how it's used in helping the player and analysing player data and generating game content. So this player retention, be keeping people in the games and the game content. Furthermore, AI has been researched and developed for use in solving complex games. And this research is having an impact on the real world. So, and particular medical research, which I'll talk about as well a little bit later on. But surprisingly, older games are still used to help us research new AI techniques. And finally, I'll look at some of the ethics, some of the, what does it might seem like AI has no ethical considerations in terms of what they do for people playing games, but there's something going on around games that's quite important, I think. So lastly, what I'll do, I'll open up my esports almanac for 2000 to 2050, and I think I'll try and let you know what I think the future holds for AI in video games. So in the distant past, so we'll go through, I'm going to go back to the beginning of AI in video games. There was a program called, there's a game called Noughts and Crosses, and a program was written to solve this game. And it even formed a twist in the 1983 movie, War Games. Shall we play a game? When I was asked to give a talk, I've got some slide things I'm just reading from. Okay, Noughts and Crosses is a game with a fixed board space and a limited number of next moves. To create an algorithm to play such a game intelligently is fairly trivial. This is also the case for other games with fixed rules and static board positions like Connect 4, Othello, chess, Go. But as you'll see, it's not only about the algorithm for these games. AI opponents in these kinds of games calculate every possible next move. And that's how you would write an algorithm to solve a game like Noughts and Crosses, Connect 4, chess, Othello. You calculate every possible next move, recording these in some kind of data structure. Then for each of these new structures, these new positions, you calculate everything that your opponent could do next. Then for each of these, you calculate how you might respond and so on. So you get a very large tree-like structure of everything that might occur at each node. A node is each branching point you see there. So that's quite easy, isn't it? You just do that. So you can work out the best next move and potentially the worst next move your opponent could take and the best next move for you, and just make sure that you're getting the best move until you get to the end of the game. And then you just work backwards from the final position to your starting position or your current position and say, right, that's the move I need to take, so that's going to definitely win for me. But if you start to work out the size of this tree of data, you'll realize it becomes very difficult to manage. I'm using that quite, it's worse than that really, I should say. So for a 4x4 board of Othello, for instance, there are nearly 10 million possible board positions. That's a 4x4 board, not a proper 8x8. For an 8x8 board, they would have 10 to the power 54 different nodes in this tree, or states of this tree. So for comparison, Noughts and Crosses has just under 20,000 board states. So even a game which is 3x3 grid and two pieces, there are about 19,000 or so board states. Therefore, if you imagine a game like chess, which has 16 different pieces on two sides of the board and 8x8 grid, the number of possible board states becomes an unimaginably large number. So we can't use these algorithms. The number of board states is just too large. So let's look at this algorithm a little bit more with regard to Noughts and Crosses. So this is how it works. So what can be done if we want to just try and get this to work in a little bit more of an efficient way? So early on in the research for AI, they talked about this algorithm I'm talking about. It's called the Minimax algorithm. You can look it up on Wikipedia. You just type Minimax into Google, you will find an interesting presentation of this. This is one about tic-tac-toe with the Minimax algorithm, as I show on the link there. And as you can see, there's a particular board state we've got here, and it's trying to maximize its position. So wherever it says +1, that means I'm winning. So I'm the player who's playing with the cross here. And then if it's a -1, that means the opponent's winning. So even though it's going to be a draw down this middle row, if you look at this here, Eventually it does reach a position where it's going to maximize. And it got to the end position, said, this is the position I want to be at, and it's got a +1 in there. So I'm going to make choices where I'm going to get the best position, my opponent's going to get a worse position. This is this min-max algorithm. And then there's a way in which you can prune this off. So this algorithm with alpha beta pruning in place will ensure the branches of the tree that some branches of this tree are not followed if they're going to be worse for you, for the player who wants to win. So it's usually the AI we're talking about here, the AI player rather than the human player. So they would just cull those branches. That makes the algorithm a little bit more efficient. But still, as I said, the size of the problem for games like Go and chess is just too large. So they can theoretically, these algorithms, create a perfect player. The amount of time and memory required to calculate and record the moves is just prohibitive. Anyway, in a commercial gaming environment, which you can imagine in the early days of video games, when they did these games like chess, early chess games, early Othello games, early noughts and crosses games, you don't want a perfect opponent because perfect opponents are not much fun for new players. So limiting this depth of the tree search, as we're talking here, makes an AI opponent weaker. And that just keeps the game interesting for some players. So a lot of the time, a less than perfect opponent is fine. That's what you're after anyway. Trying to find a perfect opponent is more of a challenge more than a goal for game developers. So what do you do when the system isn't so perfect and time is not available to calculate the best next move? This is a dilemma for the highly interactive video game. The computer needs to be able to give the adversary a move to make, which is going to challenge the player. The most common system for this is some predefined decision tree. A decision tree can be as simple as complex as is required by the game. The algorithm captures a set of data from the current game situation, so it senses the world. It then calculates what it ought to do next. It thinks about its next good move. And it uses we'll see in a moment, it uses this concept of a decision tree. And finally, it might change what it's going to do. And I'll say might, it might carry on doing what it was doing before. So it might change what it's going to do, and it reacts. So remember that in highly interactive games, the game situation is changing many times a second. So from something as simple as Pac-Man or Space Invaders, well, Space Invaders is slightly different, but Pac-Man with the ghosts that run around, to more modern games, we've got opponents, bot-type opponents attacking you. That is still that same idea of sensing, thinking, reacting within a very limited time frame. So most games run at 60 frames a second. The AI within the algorithm, within the computer game may run slower than that. So it's actually only updating itself once every other frame, every alternate frame. So it might be 30 times a second. And on some consoles now, the frame time is doubled. So it's like 120 frames a second with newer TVs and newer monitors and newer game consoles. So the amount of time they've got is getting smaller and smaller, but the processors are getting faster and faster. But it's still this problem of how much you can do for the AI update in that short amount of time. So let's look at an example of this, because I was saying this thinking part is the hard bit. You can imagine sensing and reacting, like see what's happening in the game and then move a control left or right or something. So here's a game called Pong. I wasn't sure whether to put an image of Pong in there, but I think some of the younger audience may not know what Pong is. It's a ping pong or table tennis. So the AI player here has a very simple thought process. It says the left and right here, but you can sort of relate that to up and down in this image. So if the ball is to the right of the paddle, then you move the paddle right. Otherwise, if the ball is to the left of the paddle, then move the paddle left. Otherwise, do nothing and the paddle stays still. Okay, so this is all it's doing. The AI is reacting immediately to changes in the game state. And it's a really simple system, but it does make a very difficult opponent to beat because the paddle can move up and down as in perfect reaction to the ball's position. Now, the way you introduce some more interesting features in this game to make it so it plays better for different players is just to change the reaction time. So you'd say the speed at which the paddles move might be slower, the ball's movement might be faster, it might go off odd angles and so on, which the paddles can't keep up with, and that makes it so that the opponent would lose a few times. But it's a bit weak as an AI, but the game itself is quite a simple game anyway. Not all games use this strategy. some game situations are much more complex than paddlers, and he has one job to do, and that's to hit the ball back. So, okay. I think I put this slide in the wrong place, never mind. So an NPC in video games tend to have multiple tasks to make them feel like. I'm going to go forward one and then come back to this one. So this is what it might look like in a real game. This is very simple, again, a simple version of a decision tree, because before that decision tree was saying I'm currently moving left, I'm currently moving right. So an NPC in video games tends to have multiple tasks which can make them appear live. Thus, they might patrol an area of the game environment, they might chase or attack the player, or they might flee the player to recover some health. The complexity of the environment changes, and so the number of things that can be sensed about the player will increase, and the possible decisions to make go larger, and the movements that can be made can be very varied. And essentially, they're all doing the same thing we just saw before, which is sense what's happening in the world, think about what you're going to do, and then react. So if I look at some of this, a player generally might be, what we got here, idling in the yellow idle thing here. And this is a state, this is a finite state machine. So when they're idling, they might idle for, if he's idle for 10 seconds, I don't know if you can see that, hopefully you can see that, but this is saying idle for 10 seconds. Then it would go to patrolling. And this would mean that the thought process in the game is thinking, I'm going to patrol. And that means it'll follow some fixed route. If it's finished its patrol route, which it says just here, it then goes back to idling, which is just standing still. And then it might go back 10 seconds, it goes patrolling again. If it sees an enemy and the health is high, it would go into attacking. And if the enemy's health goes low, it goes to fleeing. And if it's no enemy visible, then go back to idling. So this state transitions is what we've got here. So alternatively, you might have a behavior stack. And this is just an alternative way of managing those decisions that are made by a computer game opponent. A finite state machine is able to sense some things within a particular state, and based on this it transitions, but with the behavior stack, it would make those decisions when it based on a priority. So it might be constantly just waiting to do things. So if it can see an opponent, it would shoot. That's its first behavior, its first priority. If it can't, then it might do one of these things like react to a sound. If it can't hear any sounds, then it reacts to shots. If it can't hear any shots, it wedges. That's this particular image I got from a paper about an AI that would follow edges, cliff edges. So it might unwedge itself from things. So the final thing it's done is wandering around. It's just it's very similar to this, but it's just using what they call a behavior stack rather than the finite state machine. So these things you can look at if you're interested in this. So what I wanted to show on that previous slide is that a lot of these states and these behaviors, it's a lot of if conditionals. If you know you're programming, you know that you're doing a lot of if statements. So this previous picture was basically saying, if I'm not in a busy state and the phone rings, then I answer the phone and enter a busy state. If I'm not in a busy state and my phone call is finished, or if I'm in a busy state and my phone call finishes, then I go into a not busy state. And those finite state machines, as you saw on my previous slide, is quite complex. But software design patterns make them easier to manage. So if you ever go around programming something like this, the reason I bring this up is I saw a finite state machine, a complex one for a video game when I was working in the video games industry. It was written with 6,000 lines of very unwieldy if then else statements. And I would not recommend that approach at all because it becomes very difficult to maintain. There are much better ways of doing it. So if you do look at finite state machines and somebody's saying, if this, then do that, if this, then do that, that's fine if it's just 2 or 3 states. If you're getting a large state machine, don't do it like that. There are called software design patterns that can help you out here. Okay. So something I didn't talk about, actually, before I go to that slide, is a form of sensing. So AI systems in game development put an emphasis on things like fast pathfinding. So when you look at a game development engine, you might have seen, oh, this particular engine, say if you've used Unreal or Unity, has a pathfinding system. Now, pathfinding returns us to that traditional aspects of AI where an optimum next move can be made based on the shortest distance to the target. So when we're talking about bots in games, it's the paths followed on the decision trees. So on these decision trees, that's what makes them intelligent. But you can add a level of intelligence, which is, I know how to get from A to B with some sense of intent. You know, we talked about intent. So we've got a couple of levels of intelligence there. One that allows us to get from A to B, which is a target we're setting for. We've got thinking. It usually isn't thinking as we're going along, because once you've picked the path, it's just an algorithm to find the shortest path. But when as I said, AI in video games is the more interesting part is this section, this here, where you've got the decision trees that are happening. Having said that, due to the complexity of games like Go and chess, heuristics will drive a decision tree to enable these games to play, to make moves more quickly with the limited amount of data they can get. Because we said they can't look hundreds of moves in the future, they can look a few moves in the future, so they do use forms of these decision making to do that. Early versions of chess would have decision trees. More modern ones are using machine learning, which I'll speak about shortly. So, this is kind of where I finished talking about AI that's in video games, really, mainly because it's a very big topic. I could have picked any part of this and gone and talked in great detail about, say, those finite state machines or decision stacks or behavior stacks, decision trees and so on. So if you are interested in getting a start in AI in video games, then there's many, many books you can read. These books have been around a long time. They're very old, 2002, 2008, the AI game programming wisdom, but they have everything that everybody's still using now to make NPCs in video games, generally speaking. And they've got AI for Games as a more recent updated book. I've not read it. I just had a look on Amazon and it looked quite interesting. Got some good reviews, so maybe have a look at that one. And then there's this gamedev.net website that you can have a look at. It's the Total Beginner's Guide to Game AI. It's a good introduction to everything you'd ever need to know about AI. Well, not everything, but a good starting point anyway. So, machine learning. Machine learning, so artificial intelligence specifically, covers a lot of subjects and lots of algorithms for making computers have some thought-like intelligence. So, but one of the most common ones, so what we're doing there is a form of AI. So another form of AI is machine learning. So the idea with machine learning is that a computer will be trained on a set of data. It will be able to make some intelligent decisions based on that trained set of data. So generally speaking, there are two forms of machine learning. I'm simplifying for the benefit of this talk. There's other kind of variations on these, but generally speaking, they've got these two forms. One where machine learning is given classified data, and by that we mean you tell it what the images are. So you give it a lot of images of, say, dogs, and say these are all dogs. And you give it a lot of images of cats, and say these are all cats. And then the algorithm is informed, then by processing thousands of those images, it will understand the features in those images that define a dog, say. And I'll show another diagram in a moment, which kind of explains a bit more what's going on with these circles and lines and arrows. Then when presented with a new image, so it's no longer in training mode, it's now in recognizing mode, it will be able to identify with some certainty if the image contains a dog or a cat. So it will be trained up so it knows what dogs and cats look like based on some input features. It will look at some features and those features become the input. And then at the output, it will either be mostly, I think this is a dog, or mostly, I think this is a cat. So for the output here is just down what should just be on one of these lines, really, let's say I'm a dog. So similarly, speech recognition in the servers that your smart speaker communicates with use this idea to identify sounds as words or groups of words. So they're doing a similar thing. They're listening to groups of words, and then the server that your smart speaker is talking to recognizes those for you. So the alternative is the unsupervised machine learning algorithms. And these are similarly fed data, and they determine their own classifications though. So they might not identify the same patterns in the data that we'd expect, but they are useful in finding hidden patterns because they're not given any predefined classifications. They just find patterns and then start to say, well, I'll call this pattern 1 and this pattern 2 and pattern 3 and so on. It's up to the data scientists who kind of determine what they think their patterns are. So human behavior is a common set of data for unsupervised learning. So the aim is to find classification of actions potentially, well, in games anyway, I'm thinking there's lots of things you can do, but in games, human behavior is a common set of data for unsupervised learning. The aim is to find classifications of actions taken by users of e-commerce websites, for example, or social media portals or news aggregation services. They automatically classify the content, so the products and the posts and stories, and then they recommend the most appropriate content for their customers based on those customers' previous purchases or likes or stories that they've read. So you can see that they don't really know what they're looking at and what they're seeing, but they know that you're one of these kinds of people. So previous people like you have liked these things, so they would recommend that maybe you would like those things too. So this is what unsupervised machine learning will do. A common form of machine learning is the artificial neural net. So neural nets are just a subset of machine learning. So machine learning and neural nets are not the same thing. One's just a subset of the other, and which you can see in this picture here. So in a simple description of an artificial neural net or an ANN, there is usually one hidden layer which classifies inputs and produces outputs. And there's a very quite a simple algorithm that goes on inside that hidden layer to weigh up the data and give preference to those inputs that match what it has learned. So you run it through training it so that this values inside these hidden layers, and then it will when you pass it new data, it will be able to match that up with what it had previously learned and what it weighs that up. So this is a kind of an example of what we call a deep learning. Deep learning basically has more hidden layers. So that's what we mean when people say this system is using deep learning. It's just using an artificial neural net with multiple hidden layers. So for in this example, input, which is blue. So if this has been trained already, and what different colors mean, I'll just use colors, but it could be this is a cat, this is a dog, this is something. So if I had a blue color here, and you wouldn't normally have same colors, this diagram is not as perfect as it could be. But the data for blue would pass through these blue nodes more easily than it would other nodes. So when it comes to the output, this one that's the blue output, so saying I've recognized blue, would have more, this would have a larger weight to it, be larger value to it. So as the outputs, some inputs will have more impact on the outputs. Thus, while all input could have some weighting on the outputs, only those which match the training will come through in abundance in the right output. I hope it kind of makes sense from this picture, but it's a bit of a busy picture just showing the idea of, I quite like this part here because it's showing that this is slightly more purple here, so it should be purple, and this is slightly more blue, so it should be blue. And then those weights kind of become larger in the ones recognizing, so then it can say I've got a large certainty that I've seen a blue thing, for example. That kind of makes a bit of sense. Okay, so these systems don't directly lend themselves to controlling NPCs in a standalone video game. Some strategies have been used in machine learning to a limited extent to help influence how units react to situations in the game. But due to their complexity and inherent cost to the performance of the game, developers, developers rarely adopt them over a bot-like decision system for which the developer has complete control. An early game which used machine learning algorithms was called Creatures. It's from 1997, and it allowed you to create real life on your computer. The player would train creatures much as they would a pet, and they could breed the pets to produce more intelligent pets. Machine learning algorithms have been extremely useful in reducing the amount of time taken to find patterns in player behavior, like those in Go and chess games, so that the next best move can be calculated more quickly. They predict future outcomes of the current board positions, so they can make the best choices what they are. So in that position where we can't know all of the future positions, like I was saying in the Minimax algorithm, they were using these predictions to get weightings for which are the best positions to move to next, because some board positions will generate a future position which has got a higher chance of winning. So by blending these visual pattern recognition now, something that's been quite useful is you can, and we're going to sort of look at some examples of these in a moment, which by blending visual pattern recognition algorithms, so the ability to see what's going on the screen, and these artificial neural network algorithms in high-performance computer systems, it's been possible to create computer players that can play esports style games. So if you're not familiar with what esports are, these are usually games played with multiple players against other groups of people or multiple players. So it's like 5-on-5 players, and they are competing in a video game to win. It's like a 5-on-5 video game, or maybe a one versus one like video game as well. So the games I'm talking about are things like Dota 2 and StarCraft 2, and these high-performance systems, like the one here I mentioned, OpenAI 5, they will be able to regularly beat human opponents. The computer performs tirelessly, quickly, and it takes unprecedented moves. And this has drawn some criticism from human players. Although the advocates of these systems have said that they focus on the outcome is less useful. So it's less useful to human players to focus on the win or loss than it is to understand why the AI is making the moves it is, and therefore the human players can learn from it. So they found that by watching the AI play the game and beat opponents, the fact that it made a certain move at a certain point, which seems completely irrational, is actually got a future benefit when human players are starting to see the reason why that future benefit is in place. So the requirements for these things are extremely high, and I'll show you some stats of these. So it's really not feasible, in my opinion, to make a standalone game that has these kind of performance ability, these kind of abilities to play strategy games. But as the performance improves, machine learning will come into AI opponents in video games, I believe, in the future. And I'm not sure how near that future is, but we'll wait and see. As I mentioned before, perfect opponents, though, are not much fun. So it's going to be quite interesting how developers of video games factor in those weaknesses into the AI, so they don't always beat you. So let's have a look at some statistics here. So this is a game like Dota. So you can see that the AI for this is not looking at the game state internally. It doesn't look inside the game to understand what's going on. It looks at the image on the screen, and it's using vision pattern recognition algorithms to determine what's going on in the game. It knows what its health is over here. It knows that certain actions are going on. It doesn't really know anything, to be honest. It's using, because it's a machine learning algorithm, it just sees these patterns change on screen. And it says, well, I prefer this pattern to be up here. And I know that if this pattern appears, then that means that I'm going to get more pattern. This pattern down here is going to change. But it's going to be a reward for me. It uses this idea of reinforcement learning. But it reinforces those things that it wants to do. And it tries to get rid of those things it doesn't want to happen, like losing lots of health. So it doesn't really know what's going on. It's just watching patterns move, and it decides, okay, this is something I prefer. Hopefully that makes sense. But to do this, so it did win. It wins the series 2 out of 0, best of 3. So this is the OpenAI 5 logo. So to do this, it has a lot of CPUs. Running 60,000 CPU cores on Azure, which Azure is a web service. The GPUs, it's running on 256 GPUs. They're the graphics processing units. Those are the ones that can do a lot of high performance data manipulation. To get this, it needed to play a lot of games against itself, probably, which comes to something like 300 years worth of play per day. So a human player would only be able to play 300, would have to play 300 years to get that kind of experience. These are two different systems. So we can see this in an order of 880 years per day or 900 years per day, counting each hero separately. So they have different heroes in the game that it has to play. So it's looking at 3.3 thousand bytes of data that's running into that neural net that we talked about. It's doing 10 observations per second. So it's got 8 million observations. I'm not sure what that means, the batch size, but it's got batches per minute, 20 batches per minute at 8 million batches per observations per batch. So you can see that this is not going to be something that can be done very easily on a home computer. So, but we always say this now, look again in 20 years' time, they're saying, oh, that's easy on a home computer. So this is kind of opening that esports almanac. So what's the point of all this, of seeing this, other than to win games? Well, as I hinted at earlier, unsupervised machine learning is useful for classifying human behavior, and as such, it can be used to create a very good opponent to strategy games. The same technique has been used as a player advisor, where the computer monitors the player's actions and compares them to actions that ought to be happening, and then it offers you a hint. In this particular one, it's saying, you're doing well, keep it up. This is not encoded directly within games at the moment, as I said, because it's just too much power required, but it links to a more powerful system. So this actually exists now. It's called Gosu Ai, and you can, it's got free things. If you do play Dota a lot, if you're one of these people who wants to play and you want some help and training, you can sign up and then you can play your game. I don't know how the system entirely works, but I know you can get on there. And it can give you some advice as you're playing. So the AI monitors the game as it happens, and without any support from the game manufacturer, it just gives you advice. So online game stores, such as Steam, if I can get this up, there we go. This is the Steam store, classify you as a game player. So based on the games you've bought and the amount of time you've devoted to a game. So they can recommend, in a similar way that you're recommending things you should do in a game. This is a lot easier. This happens now. It's very much easier than kind of watching the whole screen and seeing what's happening in the game. But on the right there, this is a recommendation system where it just looks at what you're buying and looks at how much time you're devoting to a game, and then it recommends similar products to you which might match your interests. Now there are, so again, that's a sort of machine, there's a much simpler machine learning system behind that can cope with hundreds of thousands of players. So the problems with such a system, as developers of video games can be left attempting to discover the quirks in the system in order to avoid having their game sit in obscurity. So you can imagine that if your game doesn't happen to come into the doesn't seem to match most people, what most people want, then that game's going to just never get recommended. But there are systems, and Steam a few years ago was saying they're going to improve their system, so it doesn't leave those games lingering in obscurity. Something else that Steam, the Valve who runs Steam, were trying to do was customers can review bomb games. A review bombing is where you put a negative review of a game because of some other reason. Maybe they've just happened to have got some something in the news that was quite poor, or maybe an influencer has decided they don't like a game, so everybody review bombs it, which makes it give negative impact on the game's recommendations. So, but these are usually short-lived, and so you get a short dip in there, people saying it's a good game, then it comes back up to, yeah, it's a good game. So AI isn't being used in this, but I noticed what they were doing was they were using graphs. So you could see the graph of positive reviews, and then you might see a little dip, and then it'll go back up to positive reviews. And that was actually much better for game players rather than having an AI system do it. But they do use AI systems to try and do the recommendation engines and to avoid that games running into obscurity. So this is, again, an AI that's not used within the video game itself, but is used in the video games industry as such. So very much like the sensing component of AI systems within games that we've already been talking about, factors about your play will be sensed by the data capture servers. So this is a picture from 2021. So that's this year. So as you play a game, several markers from your analytical data will be fed into an algorithm, which will have been trained on your previous data, or lots of players' data. Remember that these are not to help you become a better player, but something more beneficial to the developers now. The training we've put that's in the game will reveal the kind of actions that retain players in the game or encourage the players to spend money. So these kind of things are what game makers want to encourage. So they encourage their machine learning to suggest courses of action which will subtly keep you playing and spending. So the longer you're there, the more advertising revenue they get, because they can throw adverts at you, and they have more opportunities to sell you their own products. And this is exactly what it's doing here. I don't know if you can see these wording, but down here it says, yeah, data scientist prepares a data test algorithms, build a model with some of your data set, and then you train it with 80% of data set. And this is all set up now for anybody who wanted to do their own player churn prediction and retention in the Amazon SageMaker. So you can actually detect what your players are doing. You need thousands of players, tens of thousands of players. You can't do it with 2 or 3 players because you don't get the training data. But once you've got tens of thousands of players, you can start to say, well, these players are leaving, and I want to, what were the ones that are staying, what were they doing? I want to sort of do more to keep players in, and the AI will just do it for you. So these things are able to trigger attention mechanisms based on the kind of things most likely to keep you playing, and that may be to display a promotional offer. Well, we've got that promotional offer, give you coins, give you items, award you new items, and so on. All of this is done without any human intervention, apart from what the data scientists do to prepare data. But once it's all set up, and there's some tweaks as we go along, I'm sure the data scientists want to keep their job so they can tweak things and make it a bit better, and players change and so on. So Amazon are clearly recognizing the importance of predicting player churn. If you don't know what churn means, churn is when a player comes to your product and then they leave, never to return. The idea is churn. Players who've churned are never going to return to your game, so you don't want that. So you want to reduce the player churn. Okay. Okay. Let's go on to the next bit. Okay, content generation. Okay, so an aspect of games which has been around for many years is procedurally generated environments and weapons. Procedural algorithms which use rules and heuristics to generate unique environments in game often use a random seed. This means that each player gets a unique experience, and it's different from your friend's experience, but it's not key to you particularly. So from early roguelike games, such as Rogue, which is in the top right there, NetHack, which I'm not showing, but no, it was a derivative of Rogue, to Dwarf Fortress, which is the game on the bottom right there, and Minecraft, which was a derivative of Dwarf Fortress. These are all using a random seed that generate a random world, and then you walk around and you can manipulate and you can dig around and things. So a game can create these unique worlds, it creates unique animals and plants and so on. And this gives a player an enormous variety of things to discover and find. So an obvious thing to do now is to calculate those levels and instead of generating a random world, use that player data that you've got and that player model, since you've been capturing all that data about the players, to generate, to calibrate that randomization and to make the game more fun for you as a player, and thus keep you, and for the developer of the game, that keeps you in the game. So it keeps you playing and keeps you retained, so you don't churn. So they might want to make the game difficulty suit you. And I've chosen some kind of world games there, but you can imagine a game like Candy Crush. They might want to develop levels that keep you, the game difficulty is not too difficult, not too easy, just to keep you playing the game. So they're not randomly generating levels, and they're not pre-built or sometimes the levels aren't pre-defined, authored, that's the word I was looking for. They're just generated randomly for you, or at least as a player, so they can give you levels that are going to be at your difficulty level, thus keeping you in the game. So research has gone into how machine learning can be used to learn the different styles of level design in video games. So from an understanding of the levels, the AI can suggest new levels, new designs for levels. And then once a new significant number of levels have been built as representative examples, a computer can create its own. So, and I've talked a little bit about Candy Crush there, but it's been done for generating music tracks for Guitar Hero and levels in Super Mario Brothers. And there's a kind of game/research project called AI Dungeon 2 that can create interactive stories based on previous stories that have been written. So none of these are particularly fast, but this idea of generating synthetic data is growing. It's a growing business, and Facebook recently acquired a synthetic data startup because if you read the article, if you just search for synthetic data startup on Facebook, you'll find that using personal data is becoming a bit awkward. So they are suggesting now that we generate. Someone needs to mute their mic. I'm going to do that. So the synthetic data is a growing business. Okay. Okay. I'll just pause there. Someone's kind of popping in and out of my ear. was I saying? Oh yeah, so synthetic data company. So this idea of synthetic data is really growing business because the privacy situation with our personal data is becoming more a factor for companies like Facebook. They are not allowed to they were recently in trouble for taking 3D model data from a service that they were working with, but they hadn't got the rights to use the data for a particular purpose they had. So they got into trouble for that. So they don't want to have that situation anymore. So they're starting to look at how you can generate synthetic data. Okay. Okay, right, let's move on. So here's some pictures of things of a game where it's randomly generated world. So that's much more advanced than things like Minecraft. So this a game called No Man's Sky. It's all generated randomly for you as a player, and then the random flora and fauna that's created gets uploaded to a server, and then other people can see your planets and see your environment. So this is randomly generated. I don't believe it generates particularly. It doesn't particularly generate things for you as a player. Okay. So, as I approach the end of this talk, I'm venturing into the realms of what might be possible. So before I go too far, I'd like to return to how video game intelligence is having a serious impact on research and society. As mentioned, the synthetic data created by games is useful in research to improve future AI algorithms. So the reason is that AI is very hungry for data. It needs thousands and thousands of inputs in order to train the systems. So Grand Theft Auto simulates large, busy cities with full drivable environments. By harnessing the busy city component, researchers of algorithms for self-drive automobiles are able to test algorithms much more quickly than they would by running them within a real car in a mock city test track or actually on real roads. So video games are used to train algorithms. So since machine learning algorithms are hungry for this data, it's just difficult to source this training data. So even so much that old video games are being used as a way of testing and comparing the effectiveness of research work. So if we all work into the same baseline, I can say, my algorithm's better at doing this in this game, better at this game. And so that gives a benchmark for people to work from. So the arcade learning environment has more than 50 classic arcade games running on a simulated Atari 2600 games console from the late 1970s, early 1980s. Researchers make use of this as the computer can sense the video output, think about how it wants to proceed, and then act to achieve a desired outcome. The computer can play many more games quickly and repeatedly over short periods of time. It took about 300 years in a day. So it can do that and learn all the time. So it proves its training. AI training is often reinforced through rewarded activity. And when an environment has no clear reward, sorry, this is a slightly different point, but AI training is often reinforced. But if there's no clear reward in an environment, then the AI needs to motivate itself. And one particular algorithm that I was looking at recently had no rewarded goal other than to be curious. So it would curiously go around trying to do things in the environment and think and it would work out for itself what was worthwhile doing, what was an interesting thing to do. Had this concept of curiousness and what was interesting, could self-motivate. So eventually managed to successfully play several levels of Super Mario Brothers just by being curious about the game. Didn't have any rewards, didn't know what to do, just wandered around the game. So other algorithms originally developed to compete against championship Go players have also been used in medicine to identify retinal disease in human patients. So this thing here about AlphaGo goes beyond board game, tackling real world problems. So that happened last year. So these algorithms originally set against playing board games and now having a real impact on the world. So this is playing GTA. We've got 5 minutes. Yeah. So this is a thing called Deep Drive, which is playing GTA. And if you look on the top left, you can see that it's looking at the view 8 frames per second. And then it's got some steering it's doing and throttling down the bottom left. So it's controlling the car. And it's doing this through a neural network. It's not doing, normally AI has a decision tree, like I need to turn left, I need to avoid a car, those kinds of things. If a car's approaching me, I need to turn. This is just probably, I'm guessing, had some training about how to drive this car. So you can watch that video in your own time. Obviously, I don't want to waste your time. So I've got another slide to look at. Skip past this. Okay. Yeah, so this is Google's DeepMind Deep Q Learning, which learned how to play Breakout. Breakout's like a game where you have to knock a ball through a wall. I'll try and skip through this a little bit. So it starts out with this, about 10 minutes of training. It's just kind of moving left and right, effectively randomly, but each time it moves, it learns whether it got a better outcome from that move or not. And eventually, after about 2 hours of playing like this, just moving left and right and learning what's a good outcome, all it's doing is saying, I need this score at the top left there to be high. And that's all it knows to do. Move around until that score gets as high as possible. After 2 hours of learning, it's just an expert player. It can't be beaten. It just won't miss the ball now. And it's not been told that it wasn't told in the same way as we saw before with that decision tree. If the balls to my left, go left, and the balls to my right, go right. It just knows now that to get a high score, I need to do this strategy. So it's worth looking at. Magic happens. So it realizes that digging a tunnel through the wall is the best thing to do. So it does that, tries to get that hole to the left, I'm imagining. Yeah, go on, to the left. So it's worked out on its own that it needs to do that. What's the best tactic? Okay. And that was just, that algorithm then, obviously it's just playing this game, but remember we can use these algorithms for doing real work, real world improvements. So last thing I wanted to do is look at some of I want to remind you of the impact that video game intelligence is having on all of us. We've only got a few minutes now, 5 minutes. So now and in the future, as far as NPCs in games, there's little impact, I would say, other than what might always be found in traditional storytelling in NPCs. So if they've got lots of guns or lots of swords or lots of things like that, then there's violence, and that's the thing we have to deal with anyway. We've had that for a long time. The problem I think that would come in with using AI and NPCs is there's very little social restraint and editorial imposed on these works, these games. So if they're automatically generating stories and generating NPCs are giving you conversations, there needs to be some restraints on what they might do. So that might be something to worry about in the future. As the content of the game and any stories I've been told are driven by more what you're interested in, but what might interest you personally. So as you play, you might show that you're interested in certain things. It'll begin to suffer from the same problems affecting social media. We've seen this all the time, the idea of this bubble or the echo chamber phenomenon. So you might start playing games that start to reinforce things you want, whether they're positive or negative. So more worryingly though, as I've demonstrated from the ability for a game with support for machine learning on a server to be able to retain and maintain your interest in order to maximize the revenue it can get from you. I think that's somewhat worrying. I don't know if I want to be playing a game and then suddenly find I'm spending money on the game and then suddenly find that I can't, that things around me are declining because I want to keep playing the game. We don't know what that means. And this is why I'm a bit worried about this. A few years ago, the concept of loot boxes was highlighted in government, both here and in the US. If you don't know what a loot box is, it's basically a little thing where you pay some credits in game currency, which you might buy for real money or earn by playing the game, and then it would give you a reward. And because it's a random chance of getting something really good, it's almost like spinning a roulette wheel. So then it became recognized that it's actually gambling because it's running a roulette wheel for money, whether it's real or earned in game, because it's time or money, isn't it? So more needs to be understood about how we are influenced by these AI-driven forces. I was going to talk here about Cambridge Analytica. Now, we all know about Cambridge Analytica, or if you don't, then it's worth looking at them up, because that's been a few years ago now, but I don't have time. If you know the story, then consider how that will impact games that people play in the future and how those players can be influenced, because they were influencing people in some of the things they were doing based on the data from Facebook. So where's my pointer gone? There it is. I mentioned how servers are used to capture player data. So it's not ever happening in the local machine. It's always happening on a server somewhere. And they process it and they offer intelligent actions to ensure players keep doing what their game makers want them to do. So I thought it might be worth considering the impact on the planet. You don't think this is a big thing, but think about what it might have on the planet of this AI activity, this sending things to and from a server. So I found this interesting diagram called the anatomy of AI, or an AI system. This is for Amazon Alexa, and this is what's involved in turning your lights on. When you say, Alexa, turn the lights on, this is kind of what's involved. And I'll sort of zoom in on a bit of it if I can. I did put a zoom in on this, but if you go and have a look for the anatomy of an AI, this whole section, this is the planet Earth down the bottom left, and there's the planet Earth on the bottom right there. And you extract a lot of resources in order to build an Amazon Alexa, and the router and the servers and all the server racks and the kind of processing machines. And then you've got all this heat generated and data generated here. This is you saying, this little top bit here is you saying, Alexa, turn the lights on. That runs down a whole system, which then has to go through multiple servers that have got this. On the bottom left here, this is, the middle bottom left, this is like the knowledge that the machine knows. This is all the training it's had, the data preparation and labeling, and this is all the AI training it has, and the data that when you send voice in, it gets and retrains it, goes on for ages. And then this goes all the way back through this system, through various skills and so on, and through the world, in order to get back to your machine, your Alexa, that then turns the lights on. And then this whole second section is how you, at end of life, these machines are going to have to be destroyed and then put, and all the materials reclaimed and all recycled and then put back in the earth and so on. So yeah, so that's just what's happening for Alexa. You think about that in video games, it's going to be the same problem. But you know, there's lots of conversations you can have on this, because when people were chopping trees down to lay telephone cables 100 years ago, 150 years ago, that was still an issue back then. Okay, so I've rushed through some of the algorithms that are used in NPC game AI. I've only talked about the outcomes of using machine learning in these various contexts. And it's a short presentation like this. It's really impossible for me to do justice of all the algorithms, but I hope I've managed to inform you how AI is used in video games. It's not just, and maybe you've been surprised by how making a better baddie is only part of the story these days. While we can make very challenging opponents, they don't need to be the best. You're not trying to always make the best. That's not fun. The future might hold personalized experiences and non-play characters that learn who you are and that react with more intelligence. And hopefully this will be a pleasant experience. And I'm hoping that is the case. Older game AI is being used to test modern algorithms and rate their effectiveness. The research into deep learning for perfect game playing is benefiting medical investigations. And I did skip over that a little bit because we're getting a bit close to the end. But most notably, the ability to use AI outside the game grid has been the biggest change economically in the last decade. Servers are chomping away at all our player data to give us the best experience that will bring in the most revenue for the game makers. How this will change the games we play? Well, I think we can already see it happening with the quality of game concepts available in hyper-casual games, which is like this one, Mow My Lawn. I just did a random search. I'm not saying this is a bad game or a good game. I just think it's a typical game for the 21st century. We were playing Pong back 30, 40 years ago. We went through a series of quite complex and quite intelligent games. I would have thought we've got a bunch of intelligent games, but now it's got these Mow My Lawn type games. But these are money spinners, really. This is what I'm sort of saying. I mean, they're highly addictive. Thank you for listening. I'll just leave this video running because it's got some of the games that are 2600 games. Thank you.
Thank you, Andrew.
Have you got any questions or anything? I mean,
yeah.
I
Does
probably
anyone
don't
have any questions for John? For Andrew. I saw John there.
But you should find you can unmute yourselves.
I may not have many answers, but I'll try my best.
If anybody wants to ask a question.
You can type it in the chat if you don't like talking. I don't mind reading.
I will just look at the chat. Okay.
I was just going to ask, sorry, I was just going to ask about the ethics side and whether the things that are happening we should be concerned about.
Well, I think, like anything, if we're not concerned, if we don't know if it's good or bad, if we haven't made a decision on it, I think we need to make decisions on these things. I think leaving it unchallenged is the worst thing we can do. I think it's worth us considering. This is what happened with loot boxes for quite a few years. Everything was just happily the developers, I don't think, knew what they were doing. They just went, they didn't realize it would have a negative impact. They just went, oh, well, this is great. We can make a load of money by putting these loot boxes in. And it was only after it'd been out there for a while that people started to say, well, actually, this is a gambling and there's children playing these games. And it's really making them, it's as similar as a gambling addiction. So it's pretty rubbish. So I think we need to, I think we're worried might be, we shouldn't be scared of it. I think we should try and push things forward. But I think we need to be challenging what we're doing at every step of the way.
Thank you, Andrew.
Yeah.
There's a question in the chat.
Yeah. Goodness knows how politicians will try and use similar systems to get people to vote for them without changing their policies. Yeah. I mean, that's the thing, isn't it? We don't know how it could be used badly. Or negatively, and it might. And as you said, with this is the thing I didn't get into with Cambridge Analytica. There was a whole problem there, was a controversy there about how some of the votes in, not necessarily in the UK, but around the world, were being altered by politicians being able to influence the public. If you watch the BBC's presentation, Panorama, I think was did, there's an article on it. It's really interesting. And next, there's no request. Yes, okay, good. That was just kind of thanking me.
Okay, I think well, a similar question, I think, related to ethics, and are there any legal issues to be worried about? I mean, considering that data is acquired and then this data are stored in servers, we don't even know where they are, or the users don't know where they are.
Well, I think with the legal side, they're trying, everybody's doing the right kinds of thing according to the law, in the sense they capture data and they anonymize it and they store it as groups of data. So it's not like it can be tracked to an individual, but it's the fact that I think this is where it might come down. I'm a bit wary about what I say because I'm only an opinion rather than any information here. But when you've got large groups of people, it's still anonymous, but then you've got saying, oh, well, the northeast of England will vote a different way to the southwest, but that's anonymous because we're not looking at individual people, but we're looking at whole areas. But that's still useful for a political or a national vote or a national change. So maybe the situation should be, we look at not only anonymizing individuals, but knowing that certain types of gathering of data could have national impact, I suppose. Legally, I think they're doing the right things, you know, but maybe we need to look at what the law, how, if that goes far enough, I suppose.
Thank you.
Let's have a look. We've got one there. I'm assuming you've watched AlphaGo. For training the model, do you think the quality of data, getting data from experienced players, or quantity of data from average players are more important to train the model to beat top players? I'm afraid, sorry, I'm not an AI specialist, unfortunately, in that sense, and the kind of machine learning specialist. So I wouldn't really know which is better, getting data from experienced players or quantity. I think generally, I would say it's a bit of both, which is sad to say. I don't like to say this because it sounds like if you were doing AI, if I was doing AI training, I want a large quantity of data, but if you've got a lot of data from average players, you're never going to improve. The way in which like unsupervised learning works is that it will just try out new ideas and it will do strange things. So it would become better, or it will play differently to an experienced player, but not necessarily worse. So if you think about the way training works, AlphaGo is going to be using kind of supervised learning. It knows what experienced players' data looks like. It knows what average player data looks like. So yeah, I'm not a specialist, I'm afraid, so I can't really give a good answer. I'm trying to give an answer, but I shouldn't really. Let's look at the next question. Can you say any more about AI understanding behavior of emotional aspects of people? Understanding behavior or emotional aspects of people. Again, you can understand anything. If we can get the data points, AI can pick out anything. If it's been told to look at people's behaviors, there is some AI. Again, this is AI generally not in video games, but there's some AI that was used in, where was it, China or Korea? Somewhere, I can't remember, China maybe. I think it was in the province of China, where they were looking at nervousness, whether people were nervous, and so they could potentially pick out people who might be terrorists because they were looking nervous in an airport or something like that. So that's looking at people's behavior and people's emotions. So it can do it. Whether how we use that in video games, it could be that you could be playing a game, it could be watching you with a camera, and it could say, oh, you're looking happy, therefore it's going to give you something, or you're looking sad. And you're playing the game, when you're really engrossed in a game, and it's a fantasy game with you and playing a soldier, or a knight or a warrior, and then you might look happy at killing things, and you might sort of build something based on your emotional response. That could come in the future, who knows? It might say you get real love interest with some characters, and it sees that you're really kind of keen with these NPCs, and it go very kind of Westworld on us. Yeah, so I think it would. That's all I can say about that. If you've seen Westworld, it's all about romance. Okay, not so much, but anyway. Are we getting close to understanding what a use of an AI would allow it to become self-aware? Well, that comes down to that philosophical question of what is intelligence and how do we know something's aware. We did the ELIZA problem. This was Alan Turing said, if you can't distinguish a human response from a computer response, then that computer is intelligent. That's how we measure intelligence. That's been done now. I mean, people can write computer programs. They've been able to do it for 20 years or so that appear intelligent enough that people can't distinguish which is the human and which is not the human. So what comes then, if you they used to say, if you can tell a computer a joke and it laughs, then you know that it's intelligent. But yeah, it's how we measure intelligence. I think, how would you measure something being self-aware? And then how do you know we're self-aware? Maybe we're just a combination of chemical reactions, who knows? Again, that's philosophical and metaphysical and whatever. Is there an environmental impact? The amount of data and resource the training requires seems enormous. Well, yes. I mean, this is what I was saying in that slide about if you do search for the anatomy of AI, of an AI system, this massive impact. It depends how. I mean, it's big for something like Amazon now, and it's using it economically. So, they're making money from it, and so every time we buy something that's paid for, but is it, ultimately, what's it cost to the planet? The amount of data stored is enormous, and this is something that's just doing voice recognition and understanding certain commands. So if you're in a game, I can imagine a situation where you're in a game and you could talk to the characters in the game. You could be running around, you go up to a character and say, oh, have you got some spare cash I can have? And they go, oh, no. And then they'll start talking to you, Then that could be an interesting game, but that's not going to happen on your PlayStation 7 or PlayStation whatever. It's going to send it off to a server, the big PlayStation server in the cloud, that then processes your message and then sends it back to your PlayStation and responds. So it'll be a long time before it's actually in the machine itself, and potentially the game developers might not want that to happen. They still want to have your data somewhere that they can tweak or they can fiddle around with it, and they can see what you're doing. So there you go. Okay, I've got a couple of direct messages which I won't read out, but yeah, they're quite pleasant. Thank you. Okay. Okay, the question
Any
was,
last question from anyone?
Yeah, okay. I mean, there was a quick question which was just direct to me, so I can answer it. It was just talking about, can languages, so you're talking about finite state machines, and in this person who sent me the message was saying that a language like Prolog was used for finite state machines to do AI, systems. So, and I was saying, we can use C++ and Java to do a finite state machine. Well, you can use C#, C++, Java, Python, anything to do a finite state machine, and it's just the data is structured in certain ways and it's managed certain ways. How that data is then moved around the machine can can be more efficient in some languages than others because it's how it stores, how it accesses that data and it stores that data. But I think you would, I mean, they have, it's all about libraries really these days. So you would say, I want to use a library which is going to give me a fast AI and Prolog-like response to these systems I'm on a setup.